Should we wait for Chris or Catherine, or?
Maybe they got scared by
Chris is gone today.
Okay.
Should we get started with the prayer?
Hey, there we go.
Classic Brett.
Bonnie, would you like to say?
Our Heavenly Father, we're very thankful for this opportunity that we have to attend BYU and to be a part of this lecture series. We're thankful for the presenters who have prepared. Please help us to understand well the presentation and let thy Spirit be with us. We love you in the series and we pray with us on Jesus Christ.
Amen. So, we've got two novice presenters who don't know much about the subject, know as much as you, maybe a little bit more, but still, don't hold back. If you have some questions, let's talk about it.
Make sure they're dumbed down.
Just give it to them.
Should we do it with the microphone if they're both presenting?
Yes. Hold it.
You can just hold it, yeah.
How close do we need to be?
Anywhere around where you have
Okay. Wow, look who's here. Okay, let's. Thank you.
clicker.
All right. Okay. Okay, so we're going to talk about ultra high pressure rocks and metamorphism. A lot of what we are going to talk about today was covered by Mike DeRay last week, unfortunately for us. And a lot of this stuff should be a review for those of you that have taken petrology and similar classes. But hopefully what we talk about today will be somewhat inspiring for you. And feel free to ask questions as we go. Kind of as an outline, we're going to talk about what is ultra-high pressure, kind of what constitutes ultra-high pressure, where does it occur, things like that. We'll talk about how retrograde metamorphism matters, why it matters, I guess I should say, when talking about ultra-high pressure metamorphism. And then we'll talk about the Dora Maida Massif, which is the location in the Western Alps that has experienced ultra-high pressure. We'll talk about a few indicator minerals for and how to recognize ultra-high pressure zones. And then we'll talk about coesite and diamond. So that's kind of our outline. So feel free to stop us as you desire. We don't have a whole lot going on, so, if you want to slow it down and ask some questions, we'd love it. We might not have an answer, though, so, we'll do our best. Okay, so what is it? Ultra-high pressure metamorphism, okay? It's metamorphic processes that stable coesite. So if we look here, this is a temperature pressure diagram, as many of us are familiar with. So generally speaking, pressures of 2.7 gigapascals and higher stabilized coesite. I know the diagram says a little bit differently, but that's kind of what we were reading online. In temperatures of 600 plus degrees Celsius, those temperatures can go up into 1,000, 1,500 degrees, maybe up to 1,500. I'm not sure the max. Joshua?
So, on this diagram, alpha quartz is pretty much all the quartz we ever see. Would there ever be a circumstance in which we get to see these other forms?
There you go.
That was a good question. Anyone else have an answer to that?
Yeah, thoughts?
Yeah.
So coesite is one of those high pressure forms. That's more often referred to as shocked quartz. You can see that in meteorite impacts.
Yep.
And it doesn't, as far as I know, at least for recent meteorite impact, it doesn't revert back to alpha quartz again.
Mm-hmm. So yeah, we see coesite, and we'll talk about that. Ryan will talk more about the history of how that was found, I think, discovered. But yeah, as far as finding these, I don't know, are these found on the Earth? Anybody know that frequently, that is? Beta quartz, chrysobolite.
I think some of the two had some
I should know this.
Alkaline quartz. So you see cristobalite and tridymite. Very, available on the surface.
And they, if you go back, they do form at very high temperatures and low pressures, situations that would not be caused by subduction, but other processes that would be high temperature, such as kind of a mid-ocean ridge situation, brings high temperatures and low pressures. I don't know specifics though, but that's kind of an idea.
Okay, so here's a little map of where we see ultra high pressure metamorphism. You don't really see much over here, but you got a lot over here in the Alps. You've got Dordogne, and there's Zermatt where we're going, then some other places in the Alps. But I also see a lot over there, Kazakhstan and over in Asia.
Why is the French National Central not pointing to France?
That is a good question. I don't know why it's named that. But this map shows where you see coesite and diamond, so we'll see more of that in a minute. Here's another pressure temperature diagram, a PT diagram. We saw this last week with Dr. Duray. We see that ultra high pressure up here starts at a very high GPA, upper 2.2, 2.4, mid temperature. Right when you get up into ultra high pressure, you start seeing coesite. You don't really see that before. So the question is, why are UHP zones so hard to identify? As we talked a couple weeks ago, you don't really see coesite in the rock record. Does anyone know why? Does anyone remember what we talked about?
Is it just because it's unstable and so it just reverts back to?
Yes. Yeah, exactly. We talked about the retrograde paths, and we'll go over that just real fast again.
Yeah, so, Mike Duray talked about retrograde metamorphism. Basically what happens if we kind of think about the life cycle of a rock, the rock, or the sand, or whatever the protolith is, the material gets buried, and as it gets buried deeper and deeper, the pressure increases, and so does the temperature. So this is kind of where it starts, at low temperature and low pressure. As it gets buried more and more, temperature and pressure increases, and then we reach a maximum pressure, which means it's at a maximum depth, right? And then at some point in time, erosion starts to take over. Instead of getting more and more buried, the erosion starts to clear it out more and more. And so the pressure starts to decrease, even though it's still getting hotter just because of the... Anyway, it continues to get hotter for a little bit while metamorphism is still happening, even though the pressure is decreasing, and then we reach a maximum pressure, and then as more and more erosion happens, the rock is brought closer to the surface where there's low temperatures and pressures.
Can you answer his question? Why does it continue to get hotter even though it's being unearthed? Speculate.
Go ahead.
A lot of materials are not perfect conductors, so it actually takes some time for the energy, the thermal energy, to get conducted from the ceramic the core.
Okay.
Yeah, for those who didn't hear, you talked about how some rocks are poor conductors, so it takes a while for them to actually reach their maximum temperature.
Yeah. So then, this is kind of an example.
Just waiting for him to answer.
I had my hand up.
Very good.
Good job, Brett. Good job.
Give full credit.
So then, some example retrograde paths would be, for those that have taken petrology, you should recognize these minerals: green schist, blue schist, amphibolite, granulite, eclogite. These are all different metamorphic, or minerals that form, rocks that form from metamorphic processes. And as pressure increases, so does temperature, and then the retrograde path brings it back down. So depending on the amount the rock is buried and the temperature to which it reaches, it can stabilize different rocks for a time, but then the retrograde metamorphism changes it back to other phases as the pressure decreases and as the temperature decreases.
And that's why when we have rocks getting up to UHP on the retrograde paths, they come back down and we don't see them anymore. But we do see indications of them in the rock.
So here's just another diagram, another pressure temperature diagram. It shows a couple of retrograde paths. I'm not going to worry about the details, but we go up here, we can see here's kind of a diamond and graphite stability barrier. So once we reach pressures of up here, and this is already up at 3 gigapascals, which is an incredible amount of pressure, that we can stabilize diamond in ultra high pressure environments, which we'll talk about here soon.
Oh, one more. Is there ultra high pressure metamorphism in Italy? That's the question we want to know if we can go and see some. Unfortunately, we were not going to go see them, but we're going to be looking at right here in the Western Alps. We're going over more to Zermatt, which is over here. But down on this western flank, you see some very little bit of ultra high pressure rocks. This is an example of what it might look like. So like I said again, here's the Western Alps, here's Dolomites right here, and then you see a little bit of ultra high pressure rocks right in this zone right here.
Is the ultra high pressure just just below the Matterhorn?
Okay.
We'll be able to look at the rocks, look at the lake, and look up at the Matterhorn. So we'll see them.
Oh, awesome.
It's easy to find equities.
Great. So here's some indicator minerals.
Right. So I don't want to talk about this. So up here we've got orthopyroxene eclogites. I read this in a paper. These are indicator minerals for ultra high pressure. Looking at the pressure temperature diagram, eclogite was way up at the top, right near where ultra high pressure was. So this is eclogite, orthopyroxene eclogite. You might see, I don't know exactly what the field trip is planned. I'm actually not going, but I wanted to learn about it. So eclogites, lead oxides are found in garnet. They're inclusions in garnet instead of titanium oxides, which is an indicator for ultra high pressure. Clinopyroxene, which is this guy right here in thin section. Rutile, you're not going to see this, but this is what rutile looks like. And then apatite. This is an apatite crystal, but really what you'll see, or what's an indicator of ultra high pressure, is apatite X solution in garnet. So little inclusions of apatite. And then this is more cosite, which is preserved. Cosite and microdiamonds are confined to rigid hosts, like garnet, clinopyroxene, and kyanite. That's how it's preserved, is because the cosite is found within garnet, surrounding garnet, and that's why it's preserved, even though it undergoes some retrograde metamorphism.
Cool. So this may look familiar to some people who've taken economic resource geology. Here's some other examples of rocks that will contain microdiamonds, especially this one down here. This one is a clinopyroxene. You can see a microdiamond right here in the center. So these are what the rocks kind of look like. So a little bit more about cosite and diamonds. These are some examples. The diamonds are microscopic. They're very small. So they kind of show us ultra high pressure metamorphism. They're kind of indicators like we talked about. So cosite and diamonds are found in such areas as here, phaneritic mountain belts. And the concept of buoyant continents resisting subduction, we learned that that's false. They do subduct. Dr. Harris told us a great seminar about that. But cosite was actually discovered in 1960 in the Verinder Crater, Arizona. So just like Colin talked about, they're seen in impact and shock environments. But it was first synthesized in 1953 in the lab. But in 1960, a scientist, I think his name is Chow, he discovered it, and he also discovered, how do you say it, schistolite? Yes. And that's also another ultra high pressure rock, and he named it actually after a Russian scientist who first synthesized it. So they, from 1960 on, yes.
calcite and diamonds aren't preserved in a rigid rock, do you know how long it takes them to deteriorate?
No idea. I'm sorry. Anybody else?
It's part of the retrograde path. Right, the pressure and temperature reach the maximum, which is where calcite is stabilized. And then as erosion happens, there's metamorphism still happening, but in the opposite direction. And that's what forces the calcite back into eclogites, into amphibolites, depending on the composition. So it's a process that takes, up to millions of years. But the exact numbers, I'm not sure. Dr. Keith, do you have any insight into that?
But we'll be seeing large 5-centimeter garnets on the shores of Lake Chignana that have diamonds and other high pressure minerals in them. And you'll be able to take some back with you and say, well, it has diamond in it, but it'll be only 5 micron drops.
Wow.
Right.
You'll be rich.
Yeah, so from 1960s on, they believed that they were only calcite was found in impact environments. But in 1984 in Italy, they discovered them in pink garnets in the Dolomita as inclusions, and also they saw them in Norway in eclogites. And then a few years later, they discovered microdiamonds in eclogites in Kazakhstan. So now they know that it's not just impact environments, but also metamorphism, deep seduction. You need to get up, like we talked about, upwards of 2.7 gigapascals in pressure and upwards of 200 kilometers in depth. So here's just a picture of the Dolomite Massif in Italy. Also diamond formation. We talked a little bit, just briefly. Here's a diagram of how they can form ultra deep diamonds, but you can see as a subduction slab is being subducted, they can start forming in there, and then if that brought back up, diamonds are included. So here's another map of some areas of diamonds where they're located. The only ones we're worried about is ultra pressure ones, and like we talked about, there's one right here in the Western Alps. They form there, but really they don't form very many places. You only see them a little bit over in Europe and in Asia. So it's very hard to find ultra pressure diamonds, the micro diamonds, because the lithosphere has to subduct so far and then come back up.
Are ultra pressure diamonds?
Yeah, so there's many different types of diamonds, like it shows here: lithospheric, super deep, alluvial. These diamonds form because they're so deep in the crust, or so deep in the mantle. And I don't know, Mike, do you have any insight on that?
Dr. Keith is the professional. He loves diamonds. So if we need to, we can ask him. But yeah, the microdiamonds we're talking about are just from the subduction of the slab, but it's still within the crust. Other diamonds can form super deep when deep within the mantle and then brought to the surface through kimberlite pipes. So it's the same diamond, it's still just carbon, but there are different processes that form it. I don't know if you wanted to add anything to that.
I haven't heard any good isotopic studies that determine where those low 5 micron diamonds come from. Carbon dioxide or some other carbon bearing source. Whatever the 5 micron size.
So if you guys want to learn more about diamonds, take economic and resource geology from Dr. Keith. It's a great class.
I didn't pay him too much.
Let's see, I think that is it. If anyone has any other questions on ultra pressure metamorphism, we're glad to try to answer them.
Yeah. Exsolution is when rocks are under high pressure but not enough to melt. And then certain parts of the rock are kind of, how do I want to say this? When kind of laminar parts of the rock are melted slightly and then they form different crystals. That's kind of what exsolution is.
Yeah, you'll learn a lot about it in petrology. I don't know if you've taken petrology yet.
We'll bring some eclogites next class to you too. And,
I think Mike DeRay brought some when he was teaching a couple last week.
there's many different types. We'll just bring you a few more samples. Very good.